Hello guys, and welcome back to my YouTube channel. In this video, I will be reviewing hydrogenation reactions, so adding H2 across a double bond. But before I get into the content, please make sure to leave a like, comment, save, and or subscribe to my channel if you find my content helpful. Love y'all! So what does a hydrogenation reaction look like? You're going to need some compound with a double bond. You're going to need H2. And you're going to need some catalyst. And now all the catalyst is going to do is motivate this double bond to attack some diatomic molecule that really isn't that reactive. And a quick refresher, diatomic molecules could be two of the same atoms, which would be homonuclear. So what we have right now, which is H2, or they could be heteronuclear. So this would be the same, or you could have two different atoms, like HBr. Diatomic homonuclear compounds are going to be nonpolar. And diatomic heteronuclear compounds are going to be polar. I just wanted to make sure everybody was on the same page with this terminology. So now let's compare this to what we've seen in the past, which is where we add some diatomic heteronuclear compound like HBr to a double bond. Because if we compare this to what we've seen in the past so far in this course, is you have some double bond which attacks a hydrogen that's attached to some electronegative atom, which in consequence makes that hydrogen delta plus, hence electrophilic, which is why the double bond attacks it via 2 in, 2 out, where we then get our carbocation intermediate. And then in the final step, the bromine, the X minus attacks that carbocation. And our final product is we added HBr to a double bond. And this can precede either a Markovnikov or an anti-Markovnikov reaction. If this is not ringing a bell, please go back to one of my previous videos. So we can see in the case of a hydrogenation reaction, this is just not the case. There is no delta plus hydrogen. Therefore, the double bond, you could think, doesn't know who to attack. Who's the electrophile? It doesn't know because the bond that exists between these two hydrogens is very stable. The electrons are shared equally between the two atoms because they are the same atom. Therefore, they do not have differing electronegativities. Therefore, there is no dipole moment. So what the catalyst does is it says, hey, double bond, go attack one of those hydrogens. It doesn't matter which one. I've gotcha. Let's just get on with it. So now let's talk about what the product of a hydrogenation reaction is. So now for the actual reaction part, all that's going to happen when you add H2 to a double bond is the double bond is going to disappear. So you just have to draw in all the original bonds, but do not draw in that double bond. And there you go. That would be the product of a hydrogenation reaction. So now I want to dive a little bit deeper into what just happened. Whenever we do a reaction, especially involving a double bond and some substrate that gets attacked by the double bond, we always ask two questions. Do we have to consider the regiochemistry? And do we have to consider the stereochemistry? And for the case of hydrogenation reactions, with respect to the regiochemistry, it's actually going to be irrelevant. It does not matter if we consider these two hydrogens to theoretically be different, H1 and H2. And the two carbons, a part of the initial bond, to be C1 and C2. And this is arbitrary labeling. And once again, this labeling is arbitrary. It's just so you and I can communicate which atom we are talking about. It doesn't matter if H1 adds to C1 or if H2 adds to C1, because you're going to get the exact same product in the end, because both hydrogens are the exact same atom. Also, one way to memorize what the product of a hydrogenation reaction is going to be is to relate the reaction to hydrogen, just like magician, but the hydrogen's magic trick is making double bonds disappear. I kind of like that one. Let's do another example. So consider the hydrogenation of this compound. Step 1 is to find the double bond. Now step 2 is to make the double bond disappear, because the hydrogen comes in and its magic trick is to make double bonds disappear. So it says, be gone, double bond. Be gone, double bond. And we get the following product. Now let's review the stereochemistry of a hydrogenation reaction. Consider this structure. We can see that there is an ethyl group on, arbitrarily labeling these carbons, C1, and there is a methyl group on C2. These two groups are different from one another. And if we compare this to the groups that were on the compounds that we previously were looking at, for example, this structure, the exact same groups were attached to each of the carbons a part of that double bond. So in this case, the stereochemistry really didn't matter. But when we have a double bond where we have different groups on at least one side of the double bond, we have to consider the stereochemistry. So what will the stereochemistry be if we perform a hydrogenation reaction on this compound? To understand the stereochemistry, I am going to do another bird analogy. So think of H2 as a bird. And I want you to think of the structure as a flying saucer, hovering over the ground. So if this is the ground, and this is the sky, this compound is a flying saucer, so it's just hovering above the ground. And this H2 is a bird. That means we're going to have two cases. The H2 can either fly in from the top and smash down on the double bond, top down, or the H2 can approach from the ground up, and smash the double bond going from the ground up. And we will get two separate products, or one product and its enantiomer. So let's go over these two products. If the H2 comes in and smashes top down, these two groups are going to have to move down. So down on a dash, D for D, down on dash. Drawing in your original structure. Removing the double bond because the hydrogen's magic trick is to get rid of the double bond. They make double bonds disappear. And now your groups, the ethyl group and the methyl group, will be on dashes. And then the two hydrogens, you don't need to draw this in, it's assumed, will be on wedges. So this would be syn addition from the top. So now consider, if the H2 comes in, starts at the ground, and it hops up and smashes up, those two groups are going to go up onto wedges. So drawing in your compound and putting both of those groups on wedges. Therefore, where would the hydrogens be? Well, they would just be on dashes. Once again, you wouldn't have to draw this in. It is assumed that the hydrogens would be on dashes. And this would be the enantiomer of the product we drew in the other case, where the hydrogen came from the sky and went top down, pushing those two groups onto dashes. Let's do one final example, but it's going to look a little different. And this question is a question that always trips up students on tests. So pretend we have this compound and we have to add D2 and some catalyst. In the same way that we can hydrogenate an alkene, we can also deuterate an alkene. So all we have to do to add D2 across an alkene is add it from the top or the bottom, just as we add H2. So it will also add syn from the top or the bottom, where we're going to get two products where they are enantiomers. So let's say the D2 comes in and adds from the top down. Top down, it's going to push those groups onto dashes. So those groups are going to be on dashes. But this time, you didn't add H2 in, you actually added D2. So you have to draw in the D's on the wedges. And then you can just say plus enantiomer, which would be the case if the D2 came in and started at the ground and went ground up, pushing those groups up onto wedges. That would be the enantiomer. All right, guys, I hope this video was helpful. Let me know if you have any questions, comments, or concerns in the comment box down below. Once again, please make sure to leave a like, comment, save, and/or subscribe to my channel if you find my stuff helpful, and leave any suggestions below in regards to what videos you want me to cover next. Love ya. Have a great night.